Excellent. So I think we'll just, we do have about 15, 20 minutes to, steal your thought process. So what we would really love to learn is how you came to this journey of using graph theory or network science. I'd like to hear from each of you how you landed up in that space. Did you always begin with network science, or did it come as a consequence of some research problem that you were investigating and you chose to look with the graph theory lens or the network science lens? So we'll have Stephen, would you like to go first?
Sure, Arathi. So I've kind of answered the question in my talk. I came to know network science because of this plague system in Kazakhstan, and I've never really heard of percolation theory or much graph theory. And we were working on this idea that the traditional theory in epidemics that contact rates increase with density, and this causes this threshold behavior we see in epidemics everywhere. But as I showed you, it's such a spatial system that the idea, the use of differential equations to model the system and have random mixing was completely inappropriate. And it was really nearest neighbor transmission that was happening. And that's, when I saw the percolation theory curve, it was like being hit over the head with it. And I took notice, and that started my journey.
Thank you, Stephen. Flora, would you like to go next?
Just found my unmute button. Yeah, because a lot of my work are on basically time series and spatial temporal data, and I'm always very interested in actually modeling activities, and actually graph structure comes just very naturally. A lot of data, even some of the public data sets, road network, for example, they are already naturally comes as a network data. Traffic data, some of them are actually rasters, spatial temporal rasters, for example, but a lot of those data are also a spatial temporal graph. And because of my recent interest on basically modeling heterogeneous information from cities, if you want to overlay, multi-source data sets, one of the best way to do that is actually through graph. So, we can actually decide on, let's say, the main graph is, either the road network or POI, places of interest graph, for example, and then you associate all the other information around it. Or, even right now, we're also thinking about modeling the human daily activities as a graph. So even individual activities as graphs as well. So if, let's say, you have sensor data, so our work, even if you look at the work I do, they come from aggregate census data from cities even, but also I work with wearable sensors, for example. So understanding this information flow from wearable sensors with people looking at their app information daily, we can also model that activity as an activity graph.
Fabulous. Flora and Kate, did you always look at graph theory?
No, I mean, I studied graph theory as an undergrad, but then didn't really do anything with it until I was developing my instance space analysis methodology. And I just recognized, so I was an editor of a journal, and I was getting pissed off with all the people who were submitting papers, which was, here's my algorithm and I tested it on 10 problems, please publish my paper kind of attitude. And so I started developing the idea of, no, we need a rigorous methodology for how we test. I chose traveling salesman problem as an example to start working on demonstrating at the instance space analysis methodology, because it's so ubiquitous and well studied. And one of the first questions in instance space analysis when you're looking at a new problem is, what can I measure about the problem that correlates with its difficulty? And so traveling salesman, it's on a graph, and you have to measure graph structure. You have to. And so I published a paper in 2012, which was a review of all the different, for many different combinatorial optimization problems, traveling salesmen, scheduling, some on graphs, some not on graphs, lots of them. what do we know in the literature about what makes these problems hard to solve? You know, bin packing, you know, the triplet ratio, you know, there's lots of things that's out there in the literature, and I pulled it all together and basically said, this is a starting point for people to start being able to measure things about their instances and make sure they have diverse instances and things. And then in the same year that I published that paper, 2012, in the same issue of Computers and Operations Research, another paper was published, which was a big computational study of graph coloring algorithms. And he had done the classic thing of some randomly generated problems and some 8 algorithms, and he reported on average. And I read that paper and thought, that's exactly the kind of work I'm trying to change. So I partnered with him. He was a mathematician in Wales. And I wrote to him and I said, how about we combine forces and you give me all your data and I measure all these interesting properties of graphs. And we collaborated together, and then that was our 2014 paper. So that was when I got really into understanding graph properties that matter.
That's wonderful, Kate. In fact, that just brings me to another point, possibly you three, if you could shed light on, network science is a very, I would say, a very broad topic applied to so many different fields. And I think an underlying aspect of working in network science is collaboration. So I just wanted, just as researchers, how has collaboration shaped your research, and especially around network science, how has it enhanced the kind of work that you do? Stephen, would you like to share a little bit around that?
I'm quite sure I understand the question, Arathi. So how has collaboration influenced my work in network science? Is that?
Yeah, so network science often is used as a tool to study a specific field, like epidemiology, criminology, algorithms, mobility patterns. So, and a key aspect of network science, and a key aspect of that would be collaboration with somebody who's possibly an expert epidemiologist. So it's really a question, like, did you have to develop those collaborations as you apply tools in network science into a specific field?
Not really. I mean, I'm a sort of a theoretical epidemiologist already, and so it's more, I took tools from network science to work in that research area. But certainly I will say it's really amazing how often you see something in another person's talk that is, they're working on a really unrelated problem, but they use something from network science that you hadn't quite appreciated or you hadn't seen before, and it jumps out at you because you can apply it to your own particular area or particular problem. Thanks. So that's all to say, congratulations on organising this. It's great to have speakers talk about their work and the opportunity to share ideas from network science.
Thank you, Steve.
I've got a question to all the speakers. So graph theory has been there for such a long time, but now because we are getting so much data and there's all these data that's available, and and then people are thinking, oh, that this is a network, that's a network, like everything, so many things are networks, and we are looking at it in more from a network lens. How is this impacting like the algorithms and the way we are going to do things? Is it going to be like, I don't know.
I'll answer that by saying, you're absolutely right. The more we get data, the more we can construct networks with a whole lot of information. And I think the applicability of graph theory has never been more obvious. At University of Melbourne, we have a Master of Data Science where the students have to work in teams on industry projects. And we had some projects from the telecommunications sector recently where they had all of the call data represented as a network, but they really wanted some help in understanding what they could do with that, because otherwise it's just a collection of data and you can arrange it as a network of which people call which people, but what else can we do with this data? And so all the graph theory measures, trying to characterize that and looking at dynamically over time of how the network structure is changing. And, we had the students learn some graph theory so they could characterize the call profile at various points in time and try to identify the critical nodes and all that kind of stuff. And so it kind of relates to the previous question about collaboration. I think there are a lot of people out there who are generating data and it can be represented automatically as graphs, but they don't necessarily know what to do with it. And so I think the role of mathematicians in these collaborations is really quite important.
Just a comment on that. So in my area, I think one of the hot topic these days is graph embedding. So I've touched on that a little bit because of time. I couldn't expand it on about that further. But there's an issue, of course, with operations on large-scale graph. So you know, things are becoming more expensive when you actually have really large-scale graph, and especially if the graphs are heterogeneous, this is even more difficult to process. So you know, Kate gave an example about call centers. You know, if you actually add other information about it, maybe demography or social relationships and all those things, right? If you want to actually combine all this information to mine them together, then you need to start to be thinking, which one is my main graph? Which one are the auxiliary information? Do we embed that on the node? Do we embed it on the relation? How do we project them to be able to get useful features, for example? So there's a lot of information like this that needs to be considered. I'm always very interested in like having to do less to achieve more. So data efficiency is one of my core research interests. So learning efficiency. So it's not efficiency in terms of time, but efficiency in terms of the number of data points needed to be able to do highly accurate inference. And in order to do that, then also another problem is, of course, sampling. So how do we sample the right information from this really large-scale graph? So that's why I think heterogeneous graph is a very hot topic these days. And there's a lot of open problem here, which is really, one is to do with processing them. So and also the right model as well. So there's a lot of deep learning network now, also a deep learning model that are actually becoming designed more just for graph structures.
Thank you, Flora, Kate, and Stephen. I think we do have time for maybe one or two questions from the audience, if anybody would like to ask any of the panelists. You could type it into the chat or you could unmute, whatever works for you.
I have another question for Kate, if I'm allowed.
Go ahead.
Just wondering if you've ever worked with species distribution models. So you go from geographical presence data to predicting the range of a species. And I know there are lots and lots of competing algorithms to do that task.
No, I haven't. You mean in terms of instance space analysis? Yeah, no. But there's no reason why, you know, the algorithms don't have to be graph coloring algorithms. You know, it could be algorithms or it could be models, and you're trying to understand the goodness of these things, you know, the model fit or whatever. So that footprint of where it's predicted to be good could be a model accuracy. It could be an algorithm's, you know, like a forecast projection or something like that. Yeah, no, that would be interesting.
Okay. I'll have to do some, you know, literature searching myself rather than just ask you.
Yeah, no, very, very happy to have a conversation about it though. It's sometimes it just needs a little bit of creativity to think about how to map what you're really asking onto the framework that we've got. Of, you know, what is an instance, what is an algorithm, might need a little bit of careful reinterpretation, but I think once you do that mapping, then the tool's there to get some insights.
Yeah.
I have a one follow-up question then for Kate as well. We're going back to my heterogeneous graph problem, right?
Yes.
So say, for example, you want to predict a certain phenomena in the city. and you have multiple graph representations from different sources, is your Matilda now capable of basically pinning and isolate the source of the graph that will be the most, basically the factors that actually contribute to the phenomena?
Yeah, so I guess you're talking about feature selection. So suppose you had, so you're saying you've got multiple graphs and you can measure multiple things about the multiple graphs. Mm-hmm. And the question is, what are the features you should measure of which graphs that are going to be most predictive of what you care about? And so what I would recommend is you've got multiple graph representations of different things, and then each one of those you could do our 18 features or more if you got creative and thought of other things that matter. So you've got 18 times how many graph representations you've got, and then it's just a big feature selection question of which of those features are going to be best to select to project to 2D to represent, so you can see the phenomenon is more predictable over here and harder to predict over here or something. Yeah.
Great. Just one thing to add also, I'm just wondering if you have had any issue aligning large-scale graphs in your Matilda. If you have actually graph, they are really large and but they need to be matched.
Matched. We don't do graph matching. No, we're just saying here's a graph and here's what we can measure about it. I can't remember what the largest, like the graph coloring, the 8,000, sorry, that was timetabling. I think we had over 10,000 graphs for the graph coloring stuff. And I can't remember what the largest size was, but it wasn't that big because we wanted to just measure lots and lots of things. And it was a huge computational study that needed to be done in a reasonable time. But that's the thing. I mean, you mentioned scalability. I mean, the bigger the graphs get, the more time it's going to take to be able to measure even a basic property of them. So it's the sort of trade-off between how much to measure versus if you're going to take forever to measure a whole bunch of graphs so you can predict how an algorithm is going to perform, you may as well just run the algorithm and see how it performs. Yeah.
So this could be a point of collaboration between us.
Good. I look forward to getting lots of emails after this.
What we could do is we have done some kind of like graph compression algorithms where whether you can actually perform either shortest path or whatever on really large scale graph, but actually what you get is you actually do it on a compressed graph instead. Mm-hmm. Yeah. And so it's the algorithm that we developed on hundreds of thousands of nodes. And the answer is actually much faster, but you still get quite a good enough answer.
Yeah.
Fascinating. Thank you so much, Flora, Kate, and Stephen, for accepting our invitation, sharing your work, and really a really engaging conversation in the panel as well. So this brings us to the end of our two-day workshop. And to wrap it up, I'd like to invite Professor Asha Rao, Associate Dean at the School of Science, to please share. She works in network science as well, and she's got a lot of research experience in that area. So Asha, over to you. Sevvandi, are you able to spotlight Asha so that she shows up?
Hold it, Arathi.
Thank you, Arathi. Just very fascinating talks. Kate, I love the way you said that past experience is not a predictor of future success. Reminds me of the way investment funds. and it is so true that we use algorithms without actually thinking about what are they checking, how are they checking. This is some of the things that I've been thinking about this year as well about assessment. Given that we have all moved away from exams, we're no longer allowed to have exams. So how do you assess the students? What are you assessing for? How are you assessing? And how do you assess them without killing yourself? Which is, I think, what most of us did last year. We just basically tried to kill ourselves. We're lucky that most of us didn't manage that. And so this year we have to look, and Flora, I was really fascinated by the work that you did with pervasive computing and Bluetooth, and remember, you were around when I was working with Money Williams and the architecture people. Yes, I was thinking, oh, I need to go and look at your papers again. Stephen, of course, I have seen your work, but it was fascinating to see that you have now graduated from gerbils to pigs. So that was really good. So thank you for all the speakers, and Robert as well in the middle, who was looking at crime, and I was really interested in what he was going to do, but it turns out he was more interested in crime within gaming, which is something I have not thought about, of how do you go from there to the real crime networks. So this wonderful workshop that was arranged by Sevvandi, Arathi, and Maria. And thank you for everybody for being a part of it. And I've got so much I want to follow up on. I think I'll have to stop sleeping for a few days to get to all of this. So I'm hoping that there will be a lot of collaboration happening because of this workshop. So thank you, everybody. Thank you for attending. And thank you, Sevvandi, Arathi, and Maria, for organizing this wonderful workshop. So let's give everybody a good hand.
Thanks, Asha. Yeah, thanks everyone. Thanks to all the speakers today.
Thank you.
Thanks, everybody. Have a great night.
Yes, and a wonderful rest of the week.
That's right.